building on day one is equal to 20 years of operational energy. So thinking about the operational embodied carbon, about the embodied carbon is important because that is day one of your building. That is a huge chunk of carbon you put in the atmosphere. Operational is a thing you do gradually over time. So I'm saying it's important, but embodied carbon is not what we're going to talk about today. Talking about operational carbon, the efficiency of the building, equipment, clean power generation, and then we'll have some case studies at the end. So to me, when you're trying to design a high performance, energy efficient design, you look at that external contact, and great, the software you're showing, it downloads all this information, it's temperature, humidity, sunlight, wind, can you do geothermal, is there air quality there? And I think it's funny, sometimes I have to have discussions with owners. I like to work with developers. Normally your universities and airports and hospitals build long-lasting, high-performance buildings. Developers tend to not want to do that because they want a return on investment 30 seconds after they open the building and they sell it. But I think that's more challenging. When you try to explain how a building can be efficient, effective, sustainable, and cost-effective, and cost-sustainable, it really hones your skills. And so tell them, you know, this is one day, Minneapolis is -20 and we're at 77 degrees, same day, that much temperature span across the country. And I cannot count how many times they have come to me and said, well, we just did a project in San Diego, same climate, so we kind of want to do the same thing. I'm like, I know you think that, but that's ASHRAE Zone 3 climate, and we're Zone 1. They're very different. And you may not perception, like I hopped off the airplane, walked the Uber, it felt nice and warm and sunny in San Diego, feels nice and warm and sunny here, they're kind of the same. Wrong. And then they have, oh, we do stuff in New Orleans. And like, New Orleans has a thing called winter. We don't have winter. Very different. So understanding the climate zone, when you look it up in the code, you're gonna need to know that. And so in our climate, and you've probably already talked about this a million times, it never really gets hot, which is really funny that we have the Miami Heat basketball team, because it gets really hot in Dallas. When you're that far away from the ocean, you can get over 100 degrees, but here, hottest day, maybe in the 90s, maybe low 90s, we don't systematically see 105, 110, 115 degrees, because we have all this water coming between us and Bimini, dampening that temperature down. So, I like this kind of graph here that says, okay, in May, it's pretty much warm and miserable 24 hours a day. Because the next question I get after, can't we just copy the design from San Diego, is, well, what we want is a lot of operable windows, because you people down here are stupid and you forgot how to use operable windows, and that's really an energy efficient way. It seems like an energy efficient way to get moisture in your sheetrock and have mold and replace it within a week or two. Sure, yeah, I'm on board with that. So, stepping back for a second to how heat transfers. Heat transfers one of three different ways. Conduction, that's when you touch a hot item and that heat transfers from solid to solid. Convection is when like a fluid or a gas phase moves by something like a hair dryer. If you're drying your hair, you have convection going on, and radiation. So the first two cannot move through the vacuum of space. So the fact that the sun is 5 bazillion degrees in temperature does not matter, because that temperature does not move through space. The only thing that moves through space is radiation. So the radiation goes through the vacuum of space, hits the planet, warms things up, including you. So the radiation is hitting you and warming you up. Conduction and convection are important when you're thinking about things like insulation. What temperature do we want our building to be inside? 75 degrees. The hottest day is 90. That's a 15-degree difference. It's completely irrelevant. We don't care about insulation. Don't go crazy with that comment. But anything above R20 in a roof, never pay back in South Florida. Where you want insulation is Boston, where it's -10 outside, and you're trying to keep it 70 degrees inside. They probably do like 65, but I'm assuming it'll be like 80 degrees in there. That's what insulation does for you. Also, building mass, which is something you guys are definitely in control of. When you go down in the Caribbean, I was down in Curacao. These funny looking houses, I thought they were ugly, oh hell, but they have very thick slabs, and they have very thick walls, at the bottom that gradually tapered up. And they just learned over hundreds of years that at night, the mass would soak up all this cool energy, and then gradually over day, it would basically wake itself out and keep the building cool. So insulation is gonna give you a time lag. So if it's sun's beating on the building, it's gonna slow that energy down so that when it gets cold at night, it's now starting to come through the wall, and that makes your building feel better. The increased mass just slows the overall curve down. So if you're in Miami, 90 degrees outside during the day, and you put a lot of insulation and you slow that heat transfer down till you get home from work, and now all of the day's heat is coming into your space, probably not a good idea. Maybe you don't want the afternoon heat coming into your space at 8 o'clock at night. So that's why I say insulation is not that important. If you're designing single family homes, which I don't do, it does, because you have so much more surface area to volume ratio. So what do we care about in this heat transfer range? Is radiation again. So solar heat gain coefficient is a factor that says at 1.0, I'm letting all the heat from the sun through radiation into the building. At 0, it's opaque and I'm blocking it all. So if you have a atrium in Miami, Fort Lauderdale, you want to let visible light through, but visible light wavelengths are different than heat causing wavelengths. So you want to let the visible light through and block the heat, so you have a low solar heat gain coefficient. Yes, you can do overhangs, yes, you can do shading, you can do all these things, but what if tree gets chopped down, whatever. Having that property in the glass does not make it dark black glass. It's not a color thing. Having a low solar heat gain coefficient just blocks that radiation. Flip side, if you're working in Denver, you want all the heat you can get. In fact, pretty much north of Orlando through the whole country, they like high solar heat gain coefficients so they can get heat during the winter and turn the heater off during the middle of the day on cold days. Rainfall, we get 64 inches of rain annually here normally. Everybody's kind of sick of rainfall right now after what we've been through in the last month or two, so I won't dwell on that. But what I would usually tell a developer is, if I gave you 5 feet of water covering your entire site, do you want to pay somebody to cram that in the ground? Or do you want to do something with it so that you don't have to go buy more water? We can clean golf carts, we can clean the railroad tracks, we can put tons of it in the air conditioning system, we can flush toilets, we can, all million different things you can do with that water, and now you're not paying for drinking water to hose off the railroad tracks or whatever. Yeah, long discussion with the Brightline people. Anyway, I won't bore you with pictures of what it looks like when you get lots of rain, because we're all familiar with that. Unlike precipitation and humidity, which is something you were also saying you could download, sometimes I get to teach at Appalachian State, which is in Boone, North Carolina, and like 12,000 feet up in the air. It is like cold all year, cold and dry. And I show them this picture of the conditions in Fort Lauderdale, and it looks like a tsunami of misery coming right at you with the oppressive and muggy and miserable. How the operable window is going to work in this situation. It's not going to make you feel any better. But yes, you can cherry pick. I have a dormitory that's closed in the summer, and everybody's at school during the day, and they're only there at night, and they can open the windows. Like, okay, I guess you can find a way to make something work in any given situation. But for the most part, in our climate, it's really difficult to make operable windows a energy saving amenity. It's a fun amenity, open the windows. So let's rethink about this one more time. You got a runner, like any athlete. The only place conduction is happening is where their toe is touching the ground. That's your only solid to solid. Convection, the airflow heat transfer, is the wind going by you, and then the evaporative heat transfer is really important if you're running, because sweat's forming on your skin, and as that sweat evaporates, it's taking energy out of your body. When you breathe out your humid air from your lungs, you're rejecting heat that way. When it's 100% relative humidity outside, your sweat doesn't evaporate, you just get wet and sticky and gooky, and you're not getting the cooling internally. You start to overheat. count how many times somebody comes up to me and says, oh, we can save a lot of energy, we're gonna do these things called swamp coolers. You ever heard of them, where we spray water and the mist lands on the people, and then when it evaporates, it cools everybody? It's like, no, in our climate, you're just gonna get everybody wet. It's not gonna do anything. But if they're the Clevelander and they're drunk, they're not gonna care, so they're not gonna notice. In Las Vegas, that mist will hit you and evaporate instantaneously and create that cooling effect. South Beach, not so much. I did have the Sunday house up in south of Palm Beach, and they had a metal roof that was like super hot. It's like 130 degrees up there, and they sprayed water on the roof, which would be hot enough to evaporate the water, and it cooled the roof off to make that roof last longer. That's a really horrific use of potable water. Other things humidity does to your building. Where does the vapor barrier go? I had a hotel on the beach. Interior design architect did not tell me. They put vinyl wallpaper on the inside of the conference rooms, and they called me a month later and they're like, well, I don't know where all this mold is coming from. I'm like, well, I know. So in a cold climate, even though it's snow outside, the moisture is inside the building. So the moisture is gonna be the moisture tries to find a balance because of the relative pressures. So if it's dry here and moist here, regardless of the wall, concrete, it doesn't care. It's just gonna go right through the wall, unless you have a vapor retarder. So if you put vinyl wallpaper on a building up north, it doesn't matter because the moisture is already in here. It's gonna stop right at the wallpaper. In the south, the vapor is outside. The humid area is outside. So the moisture is trying to go this way. And so you've air conditioned the daylights out of your room in here, and it's nice and dry and cold, and that moisture is going, oh, I'm gonna go right through the stucco, right through the concrete, like it's not even there. And then if you have a vapor barrier here, like a vinyl wallpaper, it's gonna stop. And what do you need for mold? Food, water, and time. Food is the back of the wallpaper. Water is coming through there, condensing in time. It's gonna be a mold disaster. So understanding humidity, inside and outside conditions helps you think about how you're gonna create your wall section, hopefully. Geothermal, brand new combined courthouse, county and city, city and county, city hall, this giant 80-story thing they were talking about. Oh, we're gonna do it with geothermal wells. Darn, they got an engineer from Kentucky, moron. Our water temperature is 80 degrees almost. So when you go up north and they have sinks that have hot and cold water, you turn on the cold water, it's been in 55-degree dirt and is now coming out of the sink cold. We don't have cold water. We have hot and warm, almost hot water. So you see a lot of sinks here with just one knob on them. So the problem is, the way geothermal works, if you take heat out of the ground in the winter and you heat your building, and in the summer, you take the heat out of the surroundings and you cram it back into that 55-degree earth. When it's always hot outside, all you're doing is cramming heat into the ground. There's no cycle. There's no pull back and push back in, take it out, and put it back. You just put it in, put it in, and put it in. And then because our water table is like 20 inches below the ground level, the water takes this heat and moves it slowly, very slowly around. So if you happen to be downstream and you go and put your own geothermal system in, now I'm pulling in your hot water because I'm downstream of you. The technology is great. It's great in Virginia and in Maryland and Tennessee and Kentucky and anywhere where you have actual seasons, where you have the give and take. Thank goodness they canceled that project. That sounds a really bad idea. Air quality. Some people are asking more and more about it. I had the Miami Board of Realtors call me and they're saying, hey, we're doing this new building next to the airport, and every realtor in town has to come here for continuing ed. And not only am I worried about the air quality of these people coming and going, I don't want to breathe the other people's air in my own building. So if they're sick, I don't want to be breathing their air, and this is right in the middle of COVID. And so it's okay, we'll design a system where you contain the air in each little room and filter it, and then you have other things going on. For the most part, we have pretty good air quality. I mean, compared to these guys and these guys. And I think most of the bad things in our air get blown over the Bahamas anyway. One of the things we are concerned about is particulate matter 2.5. So they used to talk a lot more about PM10, 10 microns, 2.5 is even smaller than that. 10 is stuff like pet dander, it's gonna get in your lungs and irritate you, and people with asthma are gonna have problems. PM 2.5 is gonna go straight through your lungs and into your bloodstream. And so, we don't have a lot of uranium mines in South Florida, but it does come out of car exhaust. So if you're monitoring the ambient air quality in South Florida, you'll see a little peak at 8 a.m. and a little peak at 5 p.m. Not so much now that everybody's doing work from home, but it's something that can be solved with filtration and different strategies. So ventilation has always been part of the code, but nobody cared. So you took whatever horrible design into the code official later. Okay, pass. We're out of here. I thought it was interesting that not only does America have a policy of measuring ambient air quality that you can pull up online and see what the air quality is anywhere in the States, you can do it internationally as well. And I was doing a little more research on it. I thought it was funny that, not funny, but I never thought that people would plan their vacations based on the air quality of where they were going. And it really surprised me that Paris and London had awful air quality. Beijing, obviously. One of the final things is good study in context is the wind. Get a little bit further south from here, down in the Caribbean, and you have the trade winds, and it is always moving from east to west, which sailors found out hundreds of years ago. We're sort of in this weird zone where it goes back and forth. We also have the diurnal wind coming in off the coast, and then on the islands that have volcanoes, you can pick up some wind as the wind tries to go up over the mountain. Bahamas, maybe not so much. Flat piece of sand with some pine trees on it. In Fort Lauderdale, it is primarily coming from the east, south, something like that, but we just don't have enough wind to really make wind energy generators work well. During the summer, you need at least 10 miles an hour to be even marginally okay. And yeah, we're more than that sometimes. But on the whole, you can go down to places like St. Lucia, Volcano Island, and where you put your wind generation device, it might work really, really well. Sunlight, obviously it's rainy in the summer, not as much sunlight, that impacts your ability to do photovoltaics. We're doing a exotic hotel in the jungles of Mexico. I was telling you about this last time, and I thought, great, we'll have PV because we're 100 miles from any utilities. You're on your own, build your own thing. We're on a mountainside looking out over the Pacific Ocean. You can see that. The architect was Bernard Ziskowicz out of Miami, and we're cooking up all these great things. When we get there and realize the tree canopy is like 150 feet up in the air. The entire site's shaded. We're not going to cut the trees down. So ixnay on the photovoltaics because they're all going to be in the shade all the time. And they said, "Oh, you can put them out on the beach." I'm like, "Yeah, no, I don't think so." And you rent your little beach hut with a photovoltaic panel over it. So in our climate, got a lot of radiation, a lot of humidity, rain and sunshine, but tidal energy, which you can get up in Boston. There's really no temperature drive, not a lot of wind. Do not do geothermal here. Now we're going to look at internal. So we kind of have a palette of colors from outside. Now we look at inside, and then we try to figure out where they match. ASHRAE standard 55 defines comfort. So you can establish temperatures and humidities and all these different things that will be comfort. Pull it up on the standard, and it takes into account humidity, airspeed, activity level. I always think our concept of what temperature we have inside a room is based on the European. We're all going to be wearing suits and ties and wigs and all this nonsense. And we could actually raise the temperatures if we changed our expectations of comfort in the space a little bit, which happens a lot more in the tropics. Have you ever heard of alesthesia? Alesthesia is a little mental game you can play with people where it's your perception of comfort. Because if I'm out in the black asphalt parking lot roasting and I go into the hotel lobby, if the hotel lobby is in the shade and it's 77 degrees, it's gonna feel cold compared to being in the sunlight, standing on the asphalt outside. Ooh, yeah, inside, this is nice. And then we will make the corridor to your hotel room, 78 degrees, because who hangs out in the corridor of a hotel? No one, you shouldn't just go to your room or leave. And then when you open the room and you go into your room, now it's like 75, 76 in there. So you're coming out of the corridor going, oh, wow, this is a nice hotel room. It's nice and cold in here. And so there is no like universal, like, this is the temperature that comfort is. It's different for every person. And in fact, ASHRAE, the Mechanical Engineers Club, says that 80% of the people are happy. That is an A+. It is impossible to get everybody to be happy. So a way to save energy is to look at your floor plan and then map out what do I think are good set point temperatures for each of these zones, instead of just saying everything needs to be 75. Bikram yoga. Check the heat up in there a little bit. Health and wellness. Are y'all familiar with WELL certification? So LEED certification gives you a scorecard for sustainability. So that I can compare my sustainable building in Miami with your sustainable building in Seattle, and we kind of have a common set of point systems that kind of understand sustainability. WELL is the same thing, but for health and wellness. It's not about energy. It's about air quality, water quality, light quality, thermal comfort, community, movement. Are you taking the stairs? Are you taking the elevator? Acoustics, a whole bunch of stuff like that. And so that, if your customer is looking for that health and wellness, that's something you have to start early in the design, because you have to start thinking about your air quality. Do I need to split my ambient ventilation coming in from my return air, because they may have completely different contaminants? If you have a fire in the Everglades, you need a different kind of filter than somebody's cooking popcorn in the microwave, and you need to cut that out. So water quality, monitoring that, light quality, just putting glass everywhere could create a glare problem, which is counterproductive to sustainability. And then I throw bioaffiliate in there. I think people's connection to nature is very, very important. So during the pandemic, we started thinking, you can't have something for everything. This filter, what if, yellow fever, who knows? What we can do is design systems that are flexible. So, oh no, there's a pandemic, take your cheap filter out and put your $200 MERV 16 filter in until the pandemic's gone. But if your casing isn't big enough for the better filter, because you bought the cheapest, smallest of everything, now you don't really have a way to adapt to, oh man, the Everglades are on fire, smells like smoke throughout the entire building, really annoying. UV uncoils, there's a whole bunch of things we can do. So we're trying to create designs that can flex with climate change and whatever thing comes along next. Air quality is tied to productivity, and then we complain a lot about the cost of energy, which in a building like this is probably a little bit less than $3 a square foot a year. To build a building like this is probably $300 and something a square foot. But if you do that over 10 years, that's about $30 a square foot a year. But if you took everybody's salary in an office, what they're paid, and divide that by the square footage, that would be about $350 a square foot per year. The point is, if you say a health and wellness building can make everybody more productive, do you believe that? Kind of hocus pocus, maybe a little bit, yeah, maybe sort of. But if I said, okay, they're lying about 20% productivity improvement, but what if it was 1%? If it was 1% of 350, that's bigger than your entire power bill. So the major corporations figured this out because they're smart a couple of years ago, and now they're looking for, hey, we want better air quality, better light quality, better water quality. We're on board with this because it really doesn't cost much more to design. This is that Miami Board of Regents. And I have like a little separate VRF air conditioning room. Everybody has their own thermostat in every single one of the main offices, and then every teaching room has its own air, its own filtration, because it's going to be different given different situations. Humidity control, all this stuff is in there. When you're up north of Gainesville, north of Orlando, in the winter, the cold is coming through the walls, and you can feel it everywhere. So it's very common for your air conditioner heater to blow the hot air and sort of coat the wall so that all of us sitting in here don't feel how cold it is outside, because that hot air is sort of taking out that effect. Again, the rules are different here. We don't have that. What we have is a lot of radiation heat coming through the glass, that if you had that northern design with the supply over there and the return over here, you would suck all that radiation heat through the room for all of us to enjoy, and then out. So what we normally do is leave a gap at the edge of the building so that the return air rises. You just take all that heat that comes in through the glass, don't let it run across the room, pull it straight up and into the ceiling, and then back to the air conditioner, and then supply air and on the inside. So you're blowing cold air in here, pushing it across the room, and taking it out at the edge of the building. So you're taking all that heat right off the glass, up and away and out of everybody's way. Sorry for the little hand-drawn picture, but you gotta do what you gotta do. This came out yesterday. We're working on this. This is AIA and HKS Architects have put together a resilience design toolkit. We're presenting this at the conference in Los Angeles in a couple of weeks. It's basically saying, it's not enough to do code. Because if somebody's gonna own a building for multiple years, it's gonna have to withstand a lot of different climate change things. So how do you get beyond that? You have to do, lines, hazards, resilience design. It basically gives you a step-by-step. It's 50 pages long, but it's a very comprehensive tool to help architects think through the process of how do I make this building resilient? Because it's different in different cities, like we've been talking about, different, how you're gonna use the building is different. And the last thing I look at from inside is people's connection to nature and biophilia, and how you integrate that nature into the space. And I'll show you some examples. There's actually a hotel chain, super high end, like $2,000 a night room. And they basically just Xerox this and put it into their corporate guidelines. Like, this is what we want out of rooms. Seen that before, probably Terrapin Bakery. So high performance design, we're integrating all these different pieces. If you look at the energy usage in a building, it's different everywhere. So in our case, more of a tropical design. It's mostly air conditioning. Other places it's heating, and this is like more of a hotel, has water heating. Typical office building, we don't have any water heating. So if you're doing a dormitory or a restaurant or something that has water, then the solar water heaters may be a great idea. But 14% of your energy is free right off the bat. Architects don't usually think of how their material selection, glass and insulation walls impacts the energy. Because when you measure energy, you usually have an electric meter and you're measuring the energy. You're not measuring the wall. So when you think of this in terms of sphere of influence, we play this game called the Energy Wizard, and we let all the architects team up and make selections about wall materials and roof materials and all these things, and they realize at no point in the game do we talk about the mechanical HVAC system. You can save probably 20% of the building's energy consumption just with good architecture. That impacts the first cost because all your systems are now 20% smaller. And it impacts the energy operation cost because operational costs are lower. So you're getting a first cost reduction and an operational cost reduction. People who've been designing single family homes for like 40 or 50 years get really mad at me. Put lots of insulation in the roof. You've been doing it wrong, but that's okay. Create an efficient envelope before you make your equipment more efficient, and then finally look for on-site energy. This is just to run through a couple of examples here. This is an office building in Boca Raton's. They were going for LEED Platinum, then they backed off to LEED Gold. But we were able to change the orientation a little bit, and that dropped about 7 tons of air conditioning, which is about $50,000. It really didn't change the energy usage. The sun's still in the same place. The building's still the same size it was before. Maybe it saved $500 or something. When you meet the energy code, you have to pick whether you're going to prescriptively meet the code, which is meet every single aspect of your design has to meet every single thing in the code. There's a performance route, which says there's a little give and take. I'm gonna run an energy model, and overall we're gonna be 20% better than the baseline. And then there's 90.1, hash rate 90, which is the hardest way, but if you're doing a LEED building, it has to be 90.1. So that's what you're gonna do. Architect's call. How much insulation do I need in the roof? Is this a prescriptive or performance compliance? What? No one checks energy compliance because you have a mechanical inspector, structural inspector, electrical inspector, plumbing inspector. There's no energy inspector because they would have to look and say, what is your structure? What is your architecture? What are your walls? And nobody does that. And furthermore, they'd have to go out to the job site, check it out during the underslab, go back out, check out the walls, go back out, check out line, go back out, check out the glass. Doesn't happen. Broward County is now implementing a methodology. They're not changing the code. They're just holding everybody accountable, making them sign off all up and down the line. And wow, are people not happy about that? So if you're just building a 2-story, 40,000 square foot dock shop with punch windows, just generic stuff, and you're like, I don't want to fool with an energy model, I just want to meet the code. You can just follow the prescriptive code and spend a little bit more money for insulation you don't need, and you'll end up buying double pane glass, insulated glass you don't really need. This is an example of running the energy model multiple times with different wall R values. Wall insulation does not change anything about your energy consumption. That is not where it is. We put usually somewhere around R11 in the walls because people gripe about the heat kind of coming through the wall, and it cuts down on nuisance complaints from tenants. Glass, that's where the whole battle is won and lost. So we want visible light coming through, maybe 60 or 70% of the visible light, because then you can turn your lights off. And these are basically heaters that have a little bit of light coming out of them. So anytime you turn off the artificial light, it's double power effective saving. Solar heat gain coefficient, if I can get it down to 26%, you cannot get to 0.26 without going to insulated glass. So the game is to do a performance-based compliance where you go with monolithic or laminated glass. Best laminated glass is going to be like 0.32, something like that, which does not meet the prescriptive code, which means you have to perform an energy model. So I normally tell my customers, you can pay me 25 or 30,000 bucks for an energy model, or you can pay a couple of million more for glass. Just tell me what you'd like to do. So taking that hit on less effective glass, but you're saving a lot of money, and then trying to figure out where else you can make up for it. This is an example of an elementary school in Orlando. We changed the shading coefficient from 0.7 to 0.25, saved $130,000 in cost up front, and saved close to $40,000 a year. So we start monkeying around with all the different properties of the glass, with the U values, with the shading coefficient, and we start looking for that sweet spot of affordability of the glass with performance. And you can't just put any piece of garbage in there because these things tend to go up exponentially. They go up, in other words, it's not a straight line. It goes up very quickly from, if it was going from 0 to 5 to 13.5, that's like a 300% jump. So somewhere in that 0.3, 0.32, 0.35 for our climate is the cost effective. Now again, if you follow prescriptive, follow the letter of the law, you're buying insulated glass, so your cost goes up. This is a building you might recognize off the 836 in Miami, Perkins and Will Atlanta office. We convinced them to take the shading coefficient from 0.75 to 0.42, which is still horrendous. And the radiation load is 30% of our load still. I don't even want to tell you what it was when the glass was 0.75. It was off the charts. When I was worried about people just baking and being miserable in this thing. And so at 0.42, they saved $500,000 in air conditioning and $125,000 extra cost of the glass because it was more expensive glass. But at the end of the day, they saved a life. They're doing close to 400 square feet per ton. So they're doing about a 20% energy savings over a typical baseline. So many times on the presentations that people are like, we're gonna put a big piazza out there and everybody's gonna sit in the sunlight and eat their sandwiches. I'm like, you've never been to Miami. So creative shading is something I think is a great way to drop the energy consumption in the building, but you still want that visible light in there. So it needs to be a creative way to do it. And this is a micro louver, and this is Seattle Public Library, and if you're familiar with that, but if you fly over the Seattle Public Library and look down it, it's opaque, like metal. If you walk at the street level, you can look right up into the glass because these little tiny louvers are in between the sheets of glass. So when you're in the building, if you're looking down, you know, like you see everything. You look up and it's opaque. It's interesting design. You might like it, you might not. I don't know. Lighting controls, don't rely on people to do things. Always a good idea. Daylight harvesting is really important in how you get that done. We've studied things like sheets of glass that have a gel in the middle. And so if you're putting a skylight above, you can disperse the skylight, the daylight, that's easy. It's when you have a room like this, it's only on the side, and you're trying to get that daylight into the space. Something like this nanogel glass will actually curve the light and spray it across the ceiling and create a more even light effect throughout the room. There's other ways of doing that, but that requires some effort when you're using daylight from the side to create an even light level in the space. This is Coral Springs City Hall, and we varied the visible light transmittance. This is the city council chamber. They didn't want any windows in there. I don't know why, but maybe they have to live in the dark or something. You can tell by the time we got the visible light transmittance up to 60, pretty much covered the whole space, and then could do daylight harvesting everywhere. This is in Wynwood, and we're going after well and lead and all this stuff. Part of well is getting good quality light into your space. And they're saying, well, we have this beautiful courtyard here. I'm like, yeah, bud. Unless the sun is coming straight down this like thing out of Star Wars here. Yeah, on the 8th floor, all green, all good, plenty of natural light. 2nd floor, not so much. So you make up for that by using lighting on the 2nd floor that matches the circadian numbers that you're trying to shoot for, right? So now your artificial light has to have the right wavelength, the right intensity to create that same sort of daylight effect. I'll show you a little bit more of that in a second. Electrochromic is great. It can get super dark, but it's always going to be insulated glass. But if you're in a competitive, developer-driven market down here, you can't afford that. So out of all these different things we talked about, orientation, glass, daylight, blah, 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 blah. Some of them make your air conditioning equipment smaller, which reduces your construction cost. And some things just make it more energy efficient to operate, but you still need the same size equipment. So that's what this graph shows us, that optimizing the orientation, the equipment got smaller, our first cost dropped, but the energy bill didn't really change. Once you know you need 100 tons of air conditioning, it doesn't matter if it's an inefficient or an efficient air conditioner, you still need 100 tons of air conditioning. So the first capital cost doesn't change. The operational cost is better. Better glass, better daylight harvesting. Those are your two big winners here. And now we're starting into getting some savings with ventilation. May or may not talk about that. So energy generation, something to keep in mind. Any kilowatt you use took 3 kilowatts of energy to make. Doesn't matter if it's coal, nuclear, gas-fired, doesn't matter, other than obviously not sunlight. We don't have any coal or gas down here, so anytime we do that, we're sending our money in Florida to somewhere else. Not a great overall plan for the state. Our average cost is 11 cents a kilowatt hour, so based on that, the payback on a photovoltaic system for like a home, let's say a 2,000 square foot, a little bit bigger home, is gonna be about 12, 13 years. Again, question everything. This is the Fort Lauderdale Airport here, and right over here is a little marina. And we put photovoltaic panels on there because when the sunlight is converted to energy, it is in DC. You have to put an inverter to change it to AC. That inverter has an inefficiency built in that costs you money for the inverter, and you lose power in that process. Ships run on DC. So we take the power, convert it straight to DC, feed it to the ships in the marina, and they have a loophole in the Florida Power and Light ironclad sue your daylights out of you clause, where they can sell, obviously they have to sell power to the ships. So putting photovoltaics on a marina is like a no-brainer, pays back instantly. This is on the south side of the cut there on the NOAA Advanced Green Technologies put this ground mounted system in there. As far as wind speed goes, again, I told you we really don't have much wind. But someone took a patent at NASA, and the problem with having two vertical turbine fans next to each other is they tend to kick wind off and screw up the performance of the other fan. This one has a little baffle in the middle so that both fans work continuously, generate power. So we're doing that for Tavistock up at Lake Nona. Hopefully have some data for you. Geothermal, we're working on a volcano down in the Caribbean, and we're taking all the heat out and using that for the building. How are we doing on time? We're doing okay? We got 10 minutes, maybe 20 minutes? Your building. When I think about loads on a building, air conditioning, mechanical, electrical loads, I think of it in terms of 20% pieces. The envelope, the glass, the lighting, the people and plugs, and the ventilation. So when we run that first analysis, if one of the things is really far out of whack, then you think, well, that's easy on where I can make some changes to fix things. So if we looked at School of Architecture here, yes, I'm that old. I did the design back in 1998 or whenever that was, 1888. There's a little bit of insulation, R20 in the roof. It's not enough to write home about, it's fine. The solar heat gain coefficient was 0.65, which was awesome in 1997. Now, that is horrific. You would never put that in. You can't really say, we're trying to save energy, so every other person needs to leave. That's really not a solution. So people and plugs, they are what they are. Lights, lights contribute. These are really good lights, so that's not a problem. When you run this whole little, crunch this whole little thing, you come out with this, and you say, well, whoops. Probably should have gone what didn't have. You can't just pick any property you want in glass and say, I want this, and this, because you tug on one and it pulls on another one, and an infinite amount of products are not available out there, especially not in every market. So we have people that sell glass in this area that are great salesmen, but the product is not that great. And there are great products, but you have to go to Chicago and tell them you want to ship this stuff down. People and plugs, you're not going to change that. Ventilation, not as bad as it could be. So it really comes down to radiation in our particular building. Just a few things I wanted to show you about this building. If you ever wonder what those louvers are on the backside, what that is if there's a floor that catches on fire, air comes in on the floors above and below. You can't suck smoke out of a building. You have to push clean air in and force it out. And so the floors above and below create what they call a sandwich effect, and the floor that's on fire evacuates up in the top. So the floor above and below are bringing clean air in, floor you're on takes the smoke out. Every square inch of a high-rise building is extremely expensive. So our air conditioning room doesn't have room to do the maintenance. If you have to do heavy maintenance to those air handlers, you just basically have to knock down a piece of the bathroom wall. It's cheaper to put some tile and sheetrock back up than to go ahead and allocate an extra 400 square feet to a room. We had efficient fixtures in the day. When we put them in, they've probably been replaced by now. This is a new building at another university, which we won't name, in Miami. And they wanted to do both sustainability and well certification. And their thought was, we got parents paying to put their students in our building. We need to give them some sort of guarantee. And this is kind of like COVID-ish area of time. Like, we need some guarantee they're not gonna get sick and because of our nasty building, which is what they had before. So we're gonna give a healthy building. It's gonna be energy efficient. We did our external analysis. We use a program called IES VE Pro. We actually battled with the state of Florida and got them to approve it as a code compliant software because it's so much better than freeware out there. We did our first energy analysis and decided that, of course, it's going to be cooling, and yes, there's going to be a lot of water heating. There's nothing really shocking there. We do use the buildings to shade each other, and there's weird like snake shape things that, I'm keeping a little total over here of energy saved. I don't know if that's big enough to see, but basically we saved 2% on playing with the massing and orientation. We reduced the quantity of glass. You can effectively daylight harvest a building with less than 30% glass, but some people like to be 100% glass, which causes all kinds of problems on energy consumption. We saved another 3% by buying better glass, and yes, we did the little dance of laminated glass that doesn't meet the prescriptive code, but we didn't use the worst product on the market, so somewhere in the middle. Daylight harvesting, 7% boost, that was a big thing. We were looking at, one of the big lows is ventilation. So we looked at a product where you pull the return air through this plant wall, and the microbes on the plants recondition the air and clean it up. So the ventilation code is about taking clean air from outside, pushing it in the room, taking all these contaminants and pushing them out through the restroom exhaust fan. Well, if you could just clean the air in the space, you wouldn't have to bring in so much humid air from outside, dehumidify it, and then punch it into the room. The equipment that dehumidifies the air is about $10 a CFM to buy and $2 a CFM to run. Big dollars in South Florida. So I thought, wow, we could do study rooms, have a vegetated wall. The other walls can be like glass, and you go in there and study, and you get clean air just going through the plants. We found out that the sump on the bottom, where all the water is that collects and goes back through the thing, created such a high humidity level in the room that we couldn't actually use that technology. But these are pictures from Canadian, a university up in Canada, I can't remember which one. But I thought it was a really cool idea to recondition the air, create a cool looking, interesting space, all that. We were able to do a little trick. Normally in each dorm room, you have like a fan coil. It's a fan and then some cold water coils or refrigerant, and you turn over the air in that space. What we did is we said, well, you gotta have a certain amount of ventilation for every room. I'm gonna push that ventilation across the coil and induce airflow because the air is moving. And we don't actually have a fan in each device. So every room has a chill beam, no fan. And because you're having to ventilate the room all the time, you're always pushing that air in. And so I met with the university and I said, number one, it's really quiet. There's no fan. I don't know if that's gonna be a problem. You can hear the people in the room next to you. And number two, because there's no fan, it doesn't recover quickly. So if 15 people go into one person's dorm room and we start having a party, it's gonna take a long time to cool that space off. And they said, first of all, we don't want any parties in the dorm, so that would be a great thing, deterrent. I was like, yeah, you're no fun. So we saved a tremendous amount of energy, and it's definitely an unorthodox way to approach dormitory design, but question everything. We do have large rooms with return ventilation, lobbies, the atriums, all these different things. And we used a machine called an Inverit, and it pulls some of the air off and cleans it, like I was telling you before, and pumps it back into the room. Saves a tremendous amount of money. So as we were adding these machines to the building, the air quality was getting better and better. The CO2 rate was gonna drop from 1,200, got down to 1,000, got down to 800. Sustainability was getting better because energy efficiency is getting better because we're pulling less ambient air in and dehumidifying it. But we reached a point about 750 parts per million of CO2 where health-wise it was getting better and better, but cost-wise, now we started having to add more and more machines and the cost started to go back up. So we found this little sweet spot where we're meeting as much of the health and wellness with as much of the sustainability and lower operational cost. But they reached a point, and that's the little graph of where they started to diverge from each other. There's other kinds of ventilation machines. I talked to a lot of customers about stormwater catchment and garages, multi-floor garages. I'm like, well, if you catch the rain and you put it into one of these, you don't have to worry about a person falling into that. So you don't need OSHA approved handrails and all this stuff. And you just put it on the 3rd or 4th floor of the garage and let gravity pull the water out, and that's, you know, $300 or $400 for that thing. And you get free watering for all your plants. Ritz-Carlton, Jamaica, they don't like it when you vary the loads. They don't like it when you use a lot of water in the day and not a lot of power, same thing. So they tell you, we're only gonna give you this much power. Flat line, all day, water, power, you get a flat line. Our plant can't handle diversity. So what you need to do is turn your generators on during the day when you have your peak load, and then turn them off at night when you don't need as much power. So we told the Ritz, when you turn your generators on, that exhaust is 800 degrees. We can buy a gizmo that circulates water and picks up that heat. And that's all the hot water you're gonna need for the hotel, for the restaurant, the showers, the laundry, the whole 9 yards. And you'll never turn these boilers on again. And they said, thanks, we don't believe you. And I said, we'll pay for it. And they said, well, if you'll pay for it, then, okay. You don't have to pay for it, we'll believe you and we'll do it. The boilers are there collecting dust, and never use them. It's all about questioning, you know, where you can get heat, what's different about this building than any other building. This is in the Panhandle of Florida. It's a LEED Platinum buildings and fitness thing. So on the east and west, they don't have a lot of windows, but on the north side, they have a lot of glass, and on the south side, they have louvers. The sun's always gonna be on the south side, so louver works great. Doesn't work so great on the east and west, but if you're ever down at the Miami Beach Convention Center, just take a look at how they did their angled fins so that you always get sunlight. Architectonica did a nice job with it. So we pulled up clear stories, and we put photovoltaics and solar water heating. And at the end of the day, we got about a 48% energy reduction. Got it to that LEED Platinum level. It's a combination. A lot of these things work together. If you buy more efficient lighting and your daylight harvesting, you don't get quite the same bump from either one by itself. Because now you're daylight harvesting and saving energy on really efficient light. So sometimes the integrated effect is not as good. We were looking at doing some stuff in Haiti, and their power at the time was 80 cents a kilowatt hour, and the developer wanted to buy the least efficient air conditioning and everything else. And I was like, no, not at 80 cents a kilowatt. It's like 8 times what we pay for power. The payback on better lighting and better air conditioning is gonna be instantaneous. I know this sounds ridiculous, but there's a Hampton Inn on Brickell in downtown Miami, south of the river. And it's like super amazing, super green. This is the 3-story lobby on the 8th floor facing north. And so you get this great view of the city, and they have clear stories, and they have recycling, and they have salinity in the pool, and they use saline for washing clothes, and there's like all kinds of cool stuff in there. The Shore Club out of Miami Beach did some cool stuff, and they have to deal with the historic nature of the building. So you can't just rip all the glass out and put better glass in. So they put another pane of glass inside the historic window. And they said everybody loved it because much quieter now, much more energy efficient now, and much more safe and secure, hurricane-proof inner glass. And they liked the idea that you could Bluetooth all the controls and everything, because now you can renovate one hotel room at a time and not like have to shut down half of the wing while you gouge up the sheetrock to run wires and do stuff. Really cool, sustainable renovation. Last case study, this is that hotel I was telling you about with the name Six Senses, which I can't tell anybody what brand hotel it is. It's funny, they have these things in Bali where the hotel room's out over the water. But if you ever go on Google Earth and you look at those really close, they're all like right next to each other. So it's not like you're out by yourself in the ocean. You neighbor like right there. I'm sure it would be fun if I win the lottery. I'll tell you how it is. What was weird is that part of Mexico is a hot, humid climate, but it never rains. I mean, very rarely rains, but the humidity is so thick, you cut it with a knife. And they wanted all of these different air quality, health and wellness. This is the thing I was telling you. They basically just Xeroxed Terrapin Bright Green's biophilic page and said, yeah, we want all this stuff. And so we looked at how to make power, and when you make power, you generate waste heat. But they need heat for the kitchen, heat for the showers, heat for laundry. Like there was just no end to the amount of places we could use the waste heat for this facility. They also like to make their own water and sell it. And we were looking at the individual rooms saying, again, it's extremely humid, like unbearable. So our air conditioner is just gonna look like Niagara Falls. I mean, the water is just pouring off of this coil 24 hours a day. Never rains, but the coil is dripping. So I looked at how I could collect the water off the air conditioner. And we were talking about piping it back to a cooling tower so that we could use it in the air conditioning system. And somebody said, you know, actually, these little individual hotel rooms scattered all around in the mountainside, it's hard to make the sewer work. Because there's like 2 people over here and 2 people over here, and you're running the sewer lines down the mountain, but we need more throughput to make this work. And so we ended up dumping the condensate into the sewer line to help make because again, we had to be our own utility plant at this building. So we needed the water to make everything happen and move along. So my original idea of photovoltaics, too many trees. My original idea of we're gonna capture the water and use it the air conditioning, no, but we need it for the plumbing. And so we're just sort of reacting to these things. And I thought it was funny. If you go to a customer and you say, do you want a circadian lighting system? They're gonna be like, what? So what does this hotel chain say? Oh, we have good day bulbs and we have good night bulbs. Good night bulbs are the orange wavelength, low intensity. Good day bulbs are high intensity, white blue light. But they don't think of it in terms, they don't use these scientific words. Like, oh yeah, daylight lights and nighttime lights. And that's in our standard. You have to do all this stuff. And this is the way it is, and we label it that way. And there are hotel rooms that are well certified with a certain package of things, like better water quality, better lighting quality, all this stuff. And you can, a lot of Marriotts are like that. It's really cool because you walk in and you say, oh, it's nighttime, and you push a button, every lamp in the room dims down and gets like an evening light color. I've been in the St. Regis over there, crawling on my hands and knees trying to figure out where the light switch is for the stupid lamps. It's nice to be able to just nighttime. So they take the coconuts on the site and make coconut oil. They have bees, they make honey. This particular chain makes their own water. They take all of these sustainable things that they do, because people pay a lot of extra money because they want to be in the weeds with it all. You know, they want the chickens running around, they want to be in the forest and everything. They're generating $30K. So we looked around and said, well, you're gonna want to have like organic food and all this kind of stuff, and we can build a garden, you know, where you drip the water through there, so you're hydroponic, so you're not having to spray and then let everything evaporate. So we gave him the idea. It's like, why don't you build a hydroponic farm and let somebody else run it? Let somebody local have that be their company. You can put some capital into it up front and build the thing cheaper than buying massive amounts of land and building sprinklers, which everything's vertical. And then they can also sell to all these other high-end hotels that are all gonna need organic fruits and vegetables, and you can be a 15% owner, whatever, I don't know. But I call it, it's like this final barrier to high performance design. It's one thing when you lower your construction cost, and another thing when you lower your operating cost. But to me, if you're not improving the fabric of the overall community, you're really falling short of what I consider high performance design. And so for the Urban Land Institute, I go around judging projects, and I can't count how many times people, I had one guy tell me, it's like, oh my God, the city was such a jerk. I mean, they made me pay for this park space outside the building, and I had to buy these stupid park benches that cost me $1 million. And then 10 minutes later, he was like, okay, so we built out for $42 million, and we sold both things for $60 million, and cleared, you know, $15 million. I'm like, and you're crying these huge tears because you had to buy a park bench and make your development not be a walled off little thing inside of itself. They actually wanted you to, you know, carry the sidewalks and integrate into the community, and you just acting like it was killing you. And then every once in a while you see something that does improve the entire community. I thought that the Miami Beach Convention Center did something interesting. And if you ask me where the front door was, I would always have a hard time telling you. But they moved the front door of the convention center from the north side to the south side because of the residential scale of the development on the north side of the convention center. All these people were having to deal with all the people and trucks and stuff coming and going and making all this racket. On the south side, there's nothing. You know, it's just something as simple as thinking through, am I making the community a better place? Yeah, lower my first cost, lower my operating cost, health and wellness for all the people in design, but is it really part of the community or not? So that'll be my little preachy slide for this. That's it. Thank you again for letting me come in, hopefully with something different this time.